Hello and welcome to our lesson on applications of solving rational equations. Finally made it to the last topic of this module, where I'm going to show you some places where we could actually use and apply the process of solving a rational equation. Now, I'm not saying that it's going to necessarily apply to your real life, although this is your real life. I will show you some places where it could be used, okay? So there are three types of problems that we're going to look at, but no matter the type, what are some general steps for solving a word problem? And I think that's what makes word problems challenging, is that there isn't one way to solve every type of problem, but there are some general steps to keep in mind when we're solving. I would say the first thing we should do is read it. Seems silly to even say that, but sometimes we just start looking for numbers and picking things apart to try to solve. But read the problem. Maybe read it twice if you need to, 3 times if you need to. And, you can mark the text along the way. So highlight important information, circle, underline. Or if you don't have a paper in front of you where you could do that, then just list out important facts along the way. Okay? Once you've read the problem, you've sort of identified important information, what you really want to do is define a variable. What is it that the problem is asking you to find that is going to be the variable in your situation? If it's possible, maybe you can organize your information. Maybe we can put it into some kind of a table, we could draw a picture, maybe we could apply some kind of a formula, and I'll show you some different scenarios there. Maybe we could just use words to organize things. And then we're going to try to use the organized information to do the hardest step, which is write an equation that models the scenario. Okay? The writing the equation is the hard part, because you could know how to solve your equation, but if your equation is wrong, it doesn't matter if you solve it correctly. So we want to be really careful with that step of writing the equation to model our scenario. Once we have the equation, the solving part should be review from the last topic, so we'll solve. And lastly, once we've solved it, we want to make sure we have a reasonable answer. Make sure we have an answer that makes sense for our problem. For example, if we're looking for generally anything in an application problem, a real world problem, and you get a negative answer, it's probably not going to make sense, okay? So make sure that your answer makes sense after you've solved, and also state it in a way that makes sense. So make sure you're answering the question in a way that makes sense, okay? So the first 3 examples we're going to look at are examples with proportional amounts or ratios that we can write for proportional amounts. And the good news with proportions, we know, is that we can cross multiply to solve, so that the easier type to solve. Alright, so it says for this first one that the ratio, which is a fancy word for fraction, the ratio of math majors to business majors at ASU is 1:5. If there are 21,000 students enrolled in the 2 departments, how many students are math majors? So let's go back in here. It says the ratio of math to business majors is 1:5. So this is math to business. It's 1:5. There are 21,000 students. That's the total number of students. And we want to know how many of them are math majors. So how many students are math majors? That's what we're going to be asked to find. So I'm going to define that as my variable, and I'm going to call it x. Okay? Now, in this problem, we're looking at 2 things. We're looking at math majors and business majors. So for these proportional amounts, and we could see they're going to be proportional amounts because we're given literally a ratio or a proportion to start with. So I'm going to write out the words for the 2 things that we're comparing, or the 2 things that we're looking at, which are math majors and business majors. And what I need to do, again, is I need to make a proportion. So 1 fraction equal to 1 fraction. So I need to make 2 fractions, for this 1 proportion. And in each of the fractions, I want to organize it so that math majors goes on the top and business majors goes on the bottom. Okay? So for my first fraction, I'm going to use the ratio that was given to me. It says math majors to business majors are 1:5 in a 1:5 ratio. So I'm going to put math majors and business majors 1:5. So remember, ratio is another word for fraction, even though it's written with a colon there. 1:5 like that, or 1:5 as a fraction would be totally fine. And that is going to equal a second fraction, which comes from the next piece. So math majors to business majors is 1:5 if we reduced it down. Now if it's not reduced, the number of math majors we're looking for in the total is going to be x, And the number of business majors in the total is going to be, what do we put here is the real question. Some of you might be thinking 21,000 is going to go here, but that wouldn't be correct because that's math and business majors all together, right? So think about this. Let's say there were 1,000 business or math majors, that would leave 20,000 business majors. Or if there were 2,000 here, that would leave 19,000 here. If there are X amount on the top, we have to subtract that from 21,000 to get to the amount that belongs on the bottom. So if we subtracted that from the 21,000, we get to the 20,000. So if there are X amount of math majors, then there are 21,000 minus X business majors. Hopefully that makes sense. Okay? Now we have our equation. All we have left to do is solve. And since this is a proportion, we're going to cross multiply. So 5 times x is going to give us 5x. And 1 times this quantity is not going to change it. So 21,000 minus x will stay the same. Now I want to add x to both sides. Oops. Let's use, how about pink? Let me add x to both sides. That's going to cancel that. And leave me with 6x equal to 21,000. And my last step is going to be to divide both sides by 6. That's going to cancel there, leaving me x equal to, let's see, 21,000 divided by 6. Sure, I could work that out in my head, but I don't want to goof anything. And 3,500. So 3,500 is what we got for x, and x we said up here, remember, was the number of math majors. So we're going to say 3,500 math majors. Okay, now we want to make sure that that is a reasonable answer. So let's just kind of verify this. If I wanted to check it, if there were 35,000 math majors, 21,000 total students, minus the 3,500 math majors would leave 17,500 business majors, and that fraction should reduce to 1 to 5 because there's a 1 to 5 ratio. So if I made 3,500 over 17,500, I do in fact get a ratio of 1 to 5. Okay, so it works, and we verified, so we got an answer that makes sense. Okay, let's try another one like that. So in the next one, we have a basketball player. He has made 21 out of 30 of his free throws this season for an average of 70%. How many consecutive free throws must be made to raise his average to an 82? So he's made 21 out of 30 free throws so far for an average of 70%. Now, this average of 70%, that is the same thing as the 21 out of 30. So I don't want to use both pieces of information since they're both representing the same thing. So I'm just going to leave the 21 out of 30 for now. Now it says, how many consecutive free throws must he make? That's the question. How many consecutive free throws must be made? That's going to be our variable to raise his average to an 82%. So an 82%, that means he's going to be making 82 out of 100 of his shots, okay, if we were to reduce that average. So just like the last one, we set up the words first, which was math to business majors. Let's set up the words here. When we say 21 out of 30 or 82 out of 100, we're talking about shots made versus shots attempted. So we have the makes, and then we have the attempts. And if you were to flip that, as long as all of your fractions are flipped, you're going to be fine. So it doesn't matter which word you start with first. But the first fraction I'm going to write is with, again, that 21 out of 30. So 21 out of 30. And then it says he's trying to raise his average to an 82%. So I know we're going to be trying to get to an 82% or an 82 out of 100. So I have two fractions. Now, there's got to be a variable in here somewhere. So it says how many consecutive free throws must he make to raise his average to an 82? So he's trying to get to this 82. And how many consecutive free throws does he have to make? So he's going to be adding X amount to the number of free throws he makes. But not only is he adding to his makes, right? In order to make those free throws, he has to also be attempting them. And he's making and attempting the same amount. if they are consecutively made, if it's one after another with no misses. So we're going to add that X amount to the top and the bottom, and now we have a proportion that we can cross multiply to solve. So here, 82 is going to distribute to 30 plus X, and then here, 100 is going to distribute to 21 plus X. So that's going to be 2,460 plus 82X equal to 2,100 plus 100X. Now I'm going to get my X's together here. So I'm going to subtract these 100 over. It's going to cancel those out. And then I'm just going to bring my work up this way. That's going to leave me, I still have 2,460. And then it's going to be minus, let's see, positive 82, negative 100 is going to be minus 18x. And then I still have the 2,100 on this side. So now let me subtract over the 2,460. Cancels that out, leaving me a negative 18x equal to a negative 360. Now I just got to divide. And I'm good. That cancels. And x is going to be equal to negative 360 divided by negative 18, which is going to be positive 20. So positive 20 was x, and x was a number of consecutive free throws that he has to make. So he has to make 20 consecutive free throws. This is not enough. Gosh, hang on. I didn't give myself enough space here. Scooch that up just a smidge. Okay, so 20 consecutive free throws. And ugly box, but whatever. Okay, now let's just make sure that that answer makes sense. I got a little bit of space over here, so I want to check that. He's got 21 free throws out of 30 free throws made right now. If he attempts the next 20 and makes them, and he's adding to his attempts and his makes, that would be 41 out of 50, and 41 out of 50 is in fact an 82%. So that checks out. Okay, that definitely works. Not so bad. And just because it's a big mess, I'm going to erase that. All right, so I have another one here that I set up for you to try. Hopefully you've seen actually a problem like this before. If you're feeling pretty good about this and you want to give it a shot, feel free to pause and try it. But if not, let's see what's happening here. So the scale drawing on a blueprint shows that a 10-foot wall is 2.5 centimeters long. And if you were to draw in a 12-foot wall, how many centimeters would it need to be? So we have a 10-foot wall that is 2.5 centimeters long. If you were to draw in a 12-foot wall, how many centimeters would it need to be? That's going to be what we're looking for here. How many centimeters for that 12-foot wall? So this time, instead of math and business majors or makes and attempts, we have inches and centimeters, or sorry, feet and centimeters on this blueprint drawing. So I'm going to go feet versus centimeters for my fractions to make my proportion. And again, if you flipped that, it doesn't matter as long as all of your fractions are matching, so that all these centimeters go together, all the feet go together. It doesn't matter if it's top or bottom. So we have a 10-foot wall. So I'm going to put 10 feet here and a 2.5 centimeter drawing of it. So 10 feet and 2.5 centimeters, one fraction. And then we have a 12-foot wall, so my second fraction is going to have a 12 on the top. And how many centimeters does it need to be? I don't know. That's where we put x. Now we can make these two fractions equal, make our proportion, cross multiply. So 12 times 2.5 is going to be 30. And 10 times x is going to be 10x. So if we divide both sides by 10, real quickly, we get our answer. And great. So x is going to equal 3. So 3 centimeters. And we're good. 3 centimeters on that blueprint. And again, if we want to check this just to make sure that it's good, 10 to 2.5 should equal 12 to 3. And let's see. 10 divided by 2.5, not 0.25, how about 2.5 is 4, and 12 divided by 3 is 4. So they both reduce to the same thing, or if we cross multiply, those cross products will be equal. Alright, so those are the easier types. Those are our proportions. The next type we're going to look at are called work rate problems. And in these work rate problems, typically we will be looking at two people or two things, two like pieces of machinery or whatever, working together to complete a task. And the amount of time that it takes for each person or thing or machine or whatever it is to complete the task has to be converted into a rate before we can make a reasonable equation with the information that we're going to be given. And then the sum of the individual rates is going to equal the rate for the people or the things working together. And the only tricky part about these types of problems is actually converting the amounts to the rates. So I want to show you how to do that. Okay? So let's just look at number 3, and then I'll explain from here. So we have a pipe that can fill a storage tank in 2 hours. Then we have another pipe that can fill the same tank in 3 hours. The question is, how long would it take both pipes working together to fill a tank? Okay, so if we were to just kind of think this out with words, we have a pipe that can fill a storage tank in 2 hours. Let's call this pipe 1. Okay, we have another pipe that can fill the same tank in 3 hours. Let's call this pipe 2. And then it says, how long would it take working together? I don't know, that's going to be X. Okay, so if I just wrote this out in words, if I said something like pipe 1 plus pipe 2 has to equal the two pipes together, would that be reasonable? I hope. That seems reasonable to me. So pipe 1 plus pipe 2 would be them working together, right? Now pipe 1 it said took 2 hours, and pipe 2 it said took 3 hours, and working together we didn't know, so we put an X there. Now if I left the equation like this, right? Pipe 1 which is 2, pipe 2 which is 3, and together would be X, do I get an answer that makes sense? Well, according to this simple equation, X would equal 5, so it would take them 5 hours working together. Hopefully you're realizing that that is a completely ridiculous answer, because, think about it, if pipe 1 takes 2 hours all by itself, and now it gets help, shouldn't it be faster? Right? If it's getting help from pipe 3, even though pipe 2 it takes 3 hours, even though pipe 2 takes longer than it does, working together, they should be faster. That's the whole point, okay? So I know I'm looking for an answer that's going to be less than 2, so this is not reasonable. And that is because, well, like I said a few minutes ago, the amount of time it takes for each person or thing to work has to be converted into a rate, where the rate for pipe 1 plus the rate for pipe 2 will equal their combined rate. So the real question is, how do I take the amount of 2 hours and the amount of 3 hours and convert those to rates? Like, how much of the job are they doing per hour? So let me deviate for a second here. Let's say that pipe 1 again takes 2 hours to complete a task. So 0 hours, 2 hours. 1 hour through the job, right? After 1 hour, so this line represents my job, okay? After 1 hour, how much of the job is done? Well, after 1 hour, half of the job has been done. So half of the job per hour is the rate, okay? Well, here's another job. Here's another job that takes 3 hours, okay? If a job took 3 hours, how much of the job would be done in 1 of those hours? Well, assuming I had drawn that to scale, that would be 1/3 of the job per hour. And so that would be the rate. And what if we did, let's say 4 hours? Let's say it took 4 hours to complete a job. How much of the job would be done in 1 of those hours? Well, that would be 1/4 of a job per hour. Maybe you're seeing the connection, okay? Now, what if a job took X hours? How much of the job would be done in 1 of those hours? So for 2 hours, it was a half of a job per hour. For 3 hours, it was 1/3 of the job per hour. For 4 hours, it was 1/4 of the job per hour. So for X hours, it would be 1/x of the job per hour. All we're doing to convert the amount to its related rate is flipping that number over. We're finding the reciprocal of that amount. The reciprocal of the amount is the related rate. If I flip 3 over 1, I get 1 over 3. Flip 4 over 1, I get 1 over 4. Flip x over 1, I get 1 over x. And it'd be similar if I had a fractional amount. So if it took 2/3 of an hour to do the job, then it would be 3/2 of jobs per hour. Okay? So back here, the reciprocal of the amount is the related rate. So the reciprocal of 2 is 1 over 2, reciprocal of 3 is 1 over 3, and the reciprocal of x is 1 over x. So if you have a whole number amount, you can just put a 1 over it. That's the reciprocal since there's a 1 under that whole number amount. So that is our equation. Those are the rates, and their combined rates will equal their combined rate. Okay? So now we have our equation. Not a proportion, but we can get common denominators to avoid having to deal with those denominators. So least common denominator here for 2, 3, and x would be 6x. So I would multiply this first fraction by 3x, multiply the second one by 2x, multiply this last one by 6. And now each of those denominators is 6x. And remember, once all of the denominators are the same, they no longer affect the problem. So we're going to proceed to solve using just the numerators. So the numerator here, which is, I'm going to come over here, 3x, and the numerator here, which is a 2x, equal to the numerator here, which is just 6. So we have 5x altogether equal to 6. And if we divide both sides by 5, divide 5, that cancels. X equals 6/5. Now, if I said how long does it take for that pipe, for the two pipes working together, would you say 6/5 hours? I don't know if you speak in fraction, but I don't, so I would say here the decimal would be more appropriate. 6 over 5 is going to be 1.2, so it's going to take about 1.2 hours for these two things working together, and I know that that's a reasonable answer. Remember, pipe 1 took 2 hours all by itself, now it gets help, so less than 2 hours, 1.2, makes sense. Okay? Now, let's look at number 4. This time together, Kara and Brooke can complete their Saturday chores in 15 minutes. Working alone, Brooke takes an hour to complete the chores. How long does it take Kara working alone? So together, it says they take, let me change colors here. It says together, they take 15 minutes. And then it says working alone that Brooke takes an hour. Now already I have an issue because I've got minutes and hours, and I don't want 2 units in one problem. So I either need to change the minutes to hours or change the hour to minutes, and I think this would be easier. Here I'm just going to say this is 60 minutes. So I got 15 minutes versus 60 minutes. Now how long does it take Kara working alone? We're going to call that x. Okay? So let me set this up in words first. We've got Kara, plus we have Brooke, and adding them would put them together. Okay? So now Kara working alone is what we were trying to find. We didn't know how long it took Kara working alone, so we can put an x here for Kara. Brooke working alone, it said took 60 minutes, so I'm going to put 60 here for Brooke. And working together, it said 15 minutes, so I'm going to put 15 here for together. Now again, if I just add this and make this equal, I'm going to end up with a negative answer, which doesn't make sense. So I need to convert these amounts to rates. So Kara is going to complete 1x of the chores per hour, or per minute in this case. Brooke will be 1/60th of the chores per minute, and then together 1/15th of the chores per minute. And that would be our equation. Okay? Now in the interest of time, I don't want this video going on for an hour. I'm going to leave this setup here, and I'm going to go through the next few problems, actually the rest of the problems, and just complete this setup. And then once I finish the video, I will go back and solve. So when you access the completed notes, you can see all of the solutions. But I just don't want this video taking an hour, okay? So we'll pause on the solving part. I'll show you the setup for each of these problems. And then when you look at the completed note sheet in Canvas, the solutions will all be there, okay? So let's continue here. And this one even says, setup, do not solve. It takes Sarah 3 times longer to complete a task than it takes Lucy. Together they can complete the task in 5 hours. How long does it take each of them working alone? So Sarah takes excuse me, 3 times longer to complete a task than Lucy. Now, the question here says how long does it take each of them? So I actually don't know how long it takes either one of them, but I don't want two variables. So I have to figure out, is Lucy the variable or is Sarah? Well, I know something about Sarah. Sarah takes 3 times longer than Lucy, and I don't know anything about Lucy. So Lucy is going to be my variable here. And Sarah takes 3 times longer would be 3x, if that makes sense. 3 times whatever Lucy is, so 3x. Together they can complete the task in 5 hours. All right, so I have Sarah plus I have Lucy, and adding them would make them together. So again, Sarah, Lucy, we didn't know, we called her x. Sarah takes 3 times longer, so 3x, and together was a whopping 5 hours. So if I just add like this, not going to be a reasonable answer. I got to convert these to rates. So 1 over 3x for Sarah, 1 over x for Lucy, 1 over 5 together. Okay, and again, I'll go through the solving part so you can see the solution in the completed notes. All right, moving along. Last 3 we're going to look at are what we call distance, rate, time problems. And distance, rate, time problems involve those 3 things. Problems where you're looking at people, or like they're riding bikes, or they're riding trains, or they're traveling in a plane, or whatever, some distance at some rate for some amount of time. And what we're going to do is organize the information into a table, because it's going to be a lot. There's going to be 2 people, or 2 bikes, or 2 trains, or 2 planes, and each of them will have a distance and a rate and a time. It's a lot of information, so we're going to try to organize into this table. And then once we get it into the table, we're going to use a formula. And hopefully we know the formula for distance, rate, and time, or at least we could reason through what it would be. So if I said you were traveling 60 miles per hour for 2 hours on the freeway, then how far would you have traveled? 60 miles per hour for 2 hours would be 120 miles, right? And so what we have here is a rate, and then we have a time. And if we multiply that rate and time, then we arrive at our distance. So distance equals rate times time. Distance equals rate times time is our distance, rate, time formula. Now, depending on the information we're given, we might want this to be in terms of another variable. So we might want this formula to be, let's say, solved for r instead of solved for d. So if this formula was solved for, instead of d equals r, t, if I wanted it to be t equals, if t had to be alone, then I would have to divide both sides by r. So t would be equal to distance divided by rate. Or if I wanted it to be solved for r, then I would have to divide the t over. So rate would be distance divided by time. So we could either use d equals rt, or r equals d divided by t, or t equals d divided by r, just depending on the situation, and I'll try to help you determine which formula we're going to apply. Okay? So looking here, it says Olivia bikes 15 miles per hour faster than John on his mountain bike. In the time that it takes Olivia to bike 80 miles, John bikes 50 miles, and we're going to find the rate for each bicyclist. So we're going to make a table out of this, and we're going to have a distance and a rate and a time for, in this case, 2 people. We have Olivia and we have John. Okay? So Olivia, distance, it shows us here 80 miles. John, distance here was 50 miles, so we can plop those in. And what else? The rate. So it says Olivia is 15 miles per hour faster than John, but we don't know anything about John's rate. So John's rate is going to be our variable. That's where we're going to put r. Now if she goes 15 miles per hour faster, so if he went 40, she would be going 55, right? Which would be extremely fast on a bike. But whatever his is, she's 15 faster, so x plus 15 here, okay? Now, all it tells us about time is that she can do the 80 miles in the same time that he can do the 50. But I don't really know how much time it takes Olivia. I don't really know how much time it takes John for these things to happen. So there's sort of an unknown there, but I don't want to introduce another variable. And this is how I know to use this version of the formula. Because the t column is our unknown here, I'm going to use my t equals formula in this case. So what I mean is, since time is equal to distance divided by rate, in this time column, I can just divide my distance of 80 by my rate of 15. Okay? And the same thing here, I can take my distance of 50 and divide by my rate of x, so that I don't have to introduce anything new into that spot. Okay? Now, since she can do this in the same time that it takes John, that means the times are equal. These times have to be the same, they have to be equal. So our equation becomes 80 over x plus 15 equal to 50 over x. Okay? Now again, in the interest of time, I'm going to do that solving on my own because the solving piece isn't really new. So that will be in the completed note sheet. And let's just try to get the setup going on this other guy here. Okay? So, a canoeist can paddle. Canoeist, I don't know if you've ever seen that word written before, it's an odd one. A canoeist can paddle 2 miles upstream on a certain river, in the same time she can paddle 6 miles back downstream. This time we have the speed of a current that is traveling at 2 miles per hour, and we have to find the speed of the canoeist. So there's only one person in this problem, but this canoeist, is traveling upstream and back downstream. So in our table, what we want to put is this canoeist trip upstream, and then the canoeist trip back downstream. Again, there's going to be a distance and a rate and a time for each trip. So the canoeist can paddle 2 miles upstream, that's a distance up to, in the same time that she can paddle 6 miles back downstream. So there's a distance down, just 6. And the speed of the current is 2 miles per hour, and we're trying to find her speed. So the speed of the canoeist is an unknown, but we also have the speed of a current. Now, I don't know if you know about current, but what's happening when you're going upstream? If you're going upstream, you're fighting the current. Whatever the current speed is going to be subtracted from your speed. It's going to slow you down. And then when you're going downstream with the current, you're going to add that current speed to your speed because it's going to speed you up. So for current, the current, it gets added or subtracted from your speed. From the whatever the canoeist, whatever it is in the problem. In this case, the canoeist. So from the rate. Okay, so we don't know how fast the canoeist is going. It's going some speed, and it's the same speed up and back. The only thing that's changing is the current. Okay, so the current upstream, because the current's 2 miles per hour, going upstream, she's going to be 2 miles per hour slower, so we're going to subtract 2. And then when she's going downstream with the current speeding her up, she's going to be 2 miles per hour faster. So we're going to add and subtract 2 from her speed. Okay, now again, the time column is empty. There's no more information to put in here. So again, that tells me to use the t equals formula, and t equals distance divided by rate. So I'm going to take my 2, put it over x minus 2. Take my 6 and put it over x plus 2. Okay? Now it says, again, it's the same time for both. That means, again, that these two trips have to be equal. So I know that the 2 over x minus 2 has to equal the 6 over x plus 2. And then we can cross multiply and solve. And I'm going to leave that if you want to try it, or you can check your work. Just check back with the completed note sheet. Okay? One more. Let's try to get it set up. So a tugboat in the Hudson River is traveling at 10 miles per hour. If it travels 24 miles upstream and 24 miles back downstream in a total of 5 hours, what is the speed of the current? So this time, the speed of the current is what we're looking for here. So we have, again, it's one tugboat in this problem that's making a trip upstream and making a trip back downstream, and there's going to be a distance and a rate and a time for each of those trips. So it's traveling, let's see, 24 miles upstream and 24 miles back down, and we know that it's traveling at 10 miles per hour. So I'm going to put 10 in each of these spots. But the speed of the current, what happens with the current? Well, remember upstream we subtract the current. In this case we don't know what it is, so we're going to minus x. And then downstream with the current speeding us up, so whatever that current speed is, we're going to add it here. So 10 plus x, 10 minus x. And in the time, it says the time is a total of 5 hours. So I have a number, but I can't exactly use that number because I don't know how much of the 5 hours was used going up, and I don't know how much of the 5 hours was used going down. So I don't want to put that in my table, which again tells me which formula to use. T equals distance divided by rate. So I'm going to put 24 over 10 minus x here, and 24, see if I can make this fit a little better, 24 over 10 minus x here, and 24 over 10 plus x here. Okay, now what I know again about these is that this takes a total of 5 hours. So in this case, these two aren't the same, but they total 5. So instead of making those two equal to each other, we're going to add the trip up, which was 24 over 10 minus x, with the trip down, which is 24 over 10 plus x, and make those two together equal to 5. And that would be the equation that we would solve to figure out the speed of the current. Okay? So there it is. Again, you can access the completed problems, the solutions to these last few on the Canvas site. And if you have any issues with any of the setups, or you want to see or get more of an explanation on the solving parts, then just reach out. I'll be here to help.